Let's look at 9.3, measures of regression and prediction intervals. A little humor there, we all regress to the mean eventually. All right, so if you go further in statistics, you'll get to do this by hand. We're not going to do that. We are going to use StatCrunch, but I just wanted to show you here that we look at lots of factors when we're doing a regression line, and we have to look at the deviation, so the deviation from the points back to the line. And we have a couple things going on. We have a total deviation, and then that is made up of an explained deviation. So that is explained by the relationship between x and y. And then we have an unexplained deviation. And so those are other factors that are going on. This is also just explaining the same thing. We are not going to calculate this by hand. We're going to use StatCrunch, but we have a total variation, and then that is made up of the explained variation plus the unexplained variation. So you'll see some wording like this, and hopefully this will help you know what that is. We've already looked at the correlation coefficient, R. We did that in 9.1, and that told us the correlation between x and y. So looking at that scatter diagram, we could see if they had a strong correlation, a weak correlation, no correlation, if it was linear, if it was positive, if it was negative. And so we also have what is called a coefficient of determination, and that is actually just R, the correlation coefficient squared, like literally in your calculator. The coefficient of determination tells us the explained variation over the total variation. So in this case down here, we took an R that was equal to 0.900. In order to find the coefficient of determination, we square that. When we square that, we get 0.810. And so what this means is that 81% of the variation in Y can be explained by the relationship between X and Y. So 81% of the variation in Y can be explained by that relationship between X and Y. The remaining 19% is unexplained, and it could be due to lots of things. A sampling error, it could just be coincidence. It could be that we have variables that are related to those two variables that we haven't even looked at yet. So lots of things going on in the unexplained. Now for us, StatCrunch is going to go ahead and give us the correlation coefficient. It's going to give us the R squared, the coefficient of determination. But if a problem only gives you the R, so like here R is equal to 0.874, we are literally just going to square that in the calculator, and that's going to give us our coefficient of determination, R squared. And then if they asked us to interpret, well, if R squared is equal to 0.764, then about 76.4% of the variation, this was actually that same data with the gross domestic product and the carbon dioxide emissions. And so 76.4% of the variation in Y, which was the carbon dioxide emissions, can be explained by the relationship between the gross domestic product and the carbon dioxide emissions. The remaining 23.6% is unexplained variation, and that, again, that could have to do with sampling error, just a coincidence, or there could be other factors, other variables that we should have looked at as well. In order for us to do a prediction interval, we have to have a standard deviation. So for regression, we're going to call that a standard error of estimate, S sub E. So it's going to be an S with a little e here. That's the standard error of estimate. Luckily, StatCrunch is going to do that for us because it can get a little fun. That and the margin of error gets a little bit time consuming. And so StatCrunch is going to take care of that. But if you see that S with the subscript of E, that is the standard deviation for, and so we also call it the standard error of estimate. Now, regression has the two variables. We've talked about this before where we, in, I forget if it was 9.1 or 9.2, we had degrees of freedom that was n minus 2. That's because we have two variables. So these are actually what we call a bivariate normal distribution. And so there's a lot more going on when you bring in another variable. So we're going to construct this prediction interval. We're going to use a t-distribution. Now, actually, StatCrunch is going to take care of that for us inside of the regression part of StatCrunch. But we do have to remember, in case we're asked, that the degrees of freedom is n minus 2. So sample size minus 2. This is the lovely margin of error. We are not going to calculate that. You can see that it's kind of crazy. We're not going to do a proof to prove why it looks like that. If you go further in math, you might get to do that. But in this class, we're going to use StatCrunch. But I do want to show you that for the prediction interval, it's the same idea as when we did the confidence interval. So we are going to have what we predicted for y minus the margin of error, just like we did with confidence intervals. We're going to put the population y in the middle, and then again on the other side we have the prediction of y, or the point estimate, and this time we're going to add e. So remember, we did this with confidence intervals where we subtracted the margin of error, we added the margin of error, and that's how we found our confidence interval. We're going to do the same thing with prediction interval. All right, so this problem has money raised, that's the x, versus money spent, the y, for all congressional campaigns for 8 recent 2-year periods, and this is in millions of dollars. Now, they already found the equation for us, and so y hat is equal to 0.956 x, so our slope is positive, and we know our line would be headed upwards, and our y-intercept is 6.644, so that's where it would cross on the y-axis. The first thing it asks me for is the coefficient of determination. I'm going to show you on the next page what that looks like inside of StatCrunch, but right now let's just interpret what we were given. And so the coefficient of determination turns out to be 0.989. And so we're going to put that in the answer block, and then it's asked you to interpret it. So remember that coefficient of determination is the fraction of variation that can be explained. Okay? The second part here is unexplained, but this is talking about when we're looking at the coefficient of determination, we're talking about the fraction of the variation that can be explained. And so we're looking at y being explained by x. Now, the second part is going to be the standard error of estimate. Again, that is going to come right from StatCrunch. It looks like S with a little e. In this case, it ended up being 25.731. So remember, this is our standard deviation in this kind of work, and it's always tied to y. So in our case, y is the money spent. Whoops, I think I hit my keyboard. Money spent. And so when they ask me to interpret the standard error of estimate of the money spent, of y, for a specific amount of money raised, we're always going to put y first, is about $1 million. Okay, so always put your y value first. Okay, so when we were first doing this problem, we would have to hit the box right here so that we could get into StatCrunch, and then let's look at the next page and look at StatCrunch. All right, so you can see my data came in because I hit those boxes. I'm going to hit regression, simple linear, put the x values, so put the money raised in for x, money spent in for y, hit compute, and we are going to get all the information we need. We would get our regression line here with our slope and our intercept. We get our correlation coefficient, which is 0.994. So very strong correlation, positive, because it's almost 1. Our R squared, or coefficient of determination, is next, and that was that 0.989. That it takes care of the fraction that's explained, and so that takes care of the explained variation. Then the next one is the estimate of error of standard deviation. That's the 25.731, which we talked about on the slide before. So everything's there for us, which is really nice. Thank you, StatCrunch. Okay, this problem's a little different. We are looking at the number of initial public offerings of stock issued in a 10-year period, and then the total proceeds of these offerings. So these are millions of dollars. So X is the number of public offerings of stock issued initially, and Y is going to be the proceeds, so the millions of dollars. We are going to find a prediction interval. Now, what's important with the prediction interval is that they have to give you 2 pieces of information. They have to give you a data value here. So they told me that we're going to do a prediction interval for the proceeds when the number of issues is 626. So that's my data value. I'm going to need that for StatCrunch. And then we need a level of significance. And so that was our 95% prediction. That means that C is equal to 0.95. So we need those 2 pieces of data when we go in to use StatCrunch. But let me just show you on this page what happens when we go to interpret. So StatCrunch is going to spit out the prediction interval for us, and that's these 2 numbers here. These are the 2 endpoints for my prediction interval. But when I go to decide which box to put my answer in, we are not going to take a chance. We want to be confident. So we're going to use B, and we're going to be 95% confident. And we're going to put our 2 endpoints in. Now, normally we would just pop those right in. However, the problem asks us to round to the nearest million. So what I'm going to have to do is take this 19,376.642. I'm going to round it to the nearest million. That would be 19,377. But then they want all of those zeros at the end. I don't know if I'm going to be able to fit the zeros here. Okay, and then the same thing for the next one. There, I'm going to round it to 56,685, but that's million, and so then I'm going to have to put all of the zeros at the end. There's only one problem that makes you do it that way. So read the fine print, because they want millions of dollars and showing all the zeros. Okay, so when we want to find that prediction interval, we are going to, again, hit this box so that all of our data comes over, and then let's look on the next page. So remember the 626 and the 95% level of significance. Okay, so I hit my box. I'm going to go to regression, simple linear, put the X in the first spot, the Y in the second. But this time I have to come all the way down here to the prediction interval. So it says prediction of Y. Notice I have to put that X value, the 626, in the first box, and then I have to put the significance level of 0.95 in the second box. At that point, now I can hit compute, and it's going to give me my prediction interval right here. And those were the numbers that we were working on the prior page. So you can see everything's in StatCrunch. It's just being careful about what you grab from where, and then making sure if you need a prediction interval to work your way all the way down so that you put the X value and the significance level in for the prediction.